Thank you, John, for inviting me here. And so, why do we want to understand the evolution of magma bodies? So the root of why I wanted to understand this was to understand how you form these very large eruptions, so-called super eruptions that erupt more than hundreds of cubic kilometers onto the Earth's surface. And what you see here in the picture is a nice sequence of these in the Southern Rockies. So my talk is structured in two parts, and it revolves around these two questions that you see here. So what is the lifetime and size of magma reservoirs, and how, once we have such magma reservoirs, how does the volatile budget evolve as the shallow magma reservoir evolves? Okay, so roughly you can categorize the views on upper crustal or shallow magma reservoirs into three categories. There's people arguing for ephemeral magma reservoirs, meaning that you inject a certain amount of magma in your upper crust, and then it either erupts or solidifies, and that's it. That's the ephemeral case. And second way of looking at it is the cold storage case, where you have a partially molten state in the upper crust, and that then rapidly assembles the melt and then erupts. And then finally, you have the warm storage case, where you always, or at least for a long time, can maintain a sort of eruptible lens within a magma mush system. And then once in a while, it erupts and produces these very large eruptions. So if we go and check out some observations of how a magma plumbing system looks like, there's certain spots in the world where you actually can walk through the entire crust. A very nice example is in Ivrea in northern Italy, where on the left here, and these sort of pinkish units are the lower crust, and then if you walk towards upwards in the graph, then you're walking upwards into the crust, into these yellow regions, which are volcanic deposits. There's also similar observations in the Southern Rockies, where you again see that sort of polybaric differentiation when you go from the lower part to the upper part in the crust. Then there's some geophysical observations of active volcanic systems, and again you see this multiple stages of magma storage in the crust. So on the left-hand side, we have some seismic inversion at Mount St. Helens, and you see these sort of two pockets, one in the lower crust and one in the upper crust. And on the right-hand side, we have a similar seismic inversion interpretation of the Yellowstone volcanic plumbing system. And again, you see this multiple storage system. So if you put all these pieces of evidence together, you come up with this sort of interpretation, is that we have this sort of mush column in the crust, and that you have these at multiple depths, you have these mobile magma bits in the crust, as already shown by John yesterday. So a very important bit to analyze the lifetime and size of these systems is using thermal models, because they can give you a first-order approximation of how much flux you need relative to the amount of molten magma that you can store. And people have done this for the lower crust, so Katrien Annen's work and Joe Dufek have looked at it. And for the lower crust, you can actually you inject basaltic magma in the lower crust, and it's fairly hot down there and also quite ductile, so it's quite favorable to store large buckets of magma, and so it's quite well accepted that you can have these very large storage zones of partially molten material in the lower crust. Then when you move to the upper crust, however, the story becomes more difficult, obviously, because it's much colder up there. And you need to actually inject a lot of magma to maintain really fast to maintain and build a magma storage zone in the upper crust. And so the critical flux in place and maintain a magma body is between 10 to the minus 3 and 10 to the minus 2 cubic kilometers per year, which is really fast. And you also have to place it in short time scale, so less than hundreds of thousands of years. The problems with that, or there's several issues with that, and the first problem is that these sort of rates do not correspond very well with the observed long-term average rate from field observations, and that's what's shown here in this graph. So the the green circles, and the sort of pinkish squares are the modeled results, and you see that they lay on the top end of the graph, and sort of the plutons and individual volcanoes fall way below that. And so one argument is that this is one of the main arguments that is used, that you have this ephemeral magma storage in the upper crust. So you actually have a pulse of magma which is at a much higher rate, and the long-term average rate doesn't really reflect the flux that actually was used to emplace the magma. The second problem that you have in the upper crust is that you actually, when you do zircon dating, you have you find that you have these very long ages of storage, or people interpret it as storage. So on the order of 400,000 years for the Fish Canyon, which is shown on the top left, and this recent paper by David Simonowski on the bottom right here shows you that for the annealing non-tuff, they find about 600,000 years of storage. So another counter-argument here is that, zircons can actually be produced much deeper in the crust, so you might be able to solve the problem like that. And a third problem with the very fast injection rate to form an upper crustal magma body is that this is mechanically really unstable. So it's going to be very, very difficult when you do things very fast to store it at any shallow depth. It should actually go directly to the surface, and shouldn't bother with staying in the like at 2 kilobars or shallower, although we have evidence that it does. So since we have this interpretation of this mush column, what we actually thought of is that you shouldn't, the idea we wanted to test is that you shouldn't just look at the upper crust as a separate entity where you inject new magma, but you should actually do the thermal modeling on the scale of the mush column itself. And so we decided to do this simplified two-stage model where you first have injection of basalt in the lower crust, and then see how that can influence the injection in the upper crust. So governing equations, so we're just solving for conservation of energy and mass. So when we're crystallizing, you have to take into account the latent heat, obviously. And to take into account the latent heat, you're using melting curves or crystallization curves. And for our crustal lithologies, we use amphibolite in the lower crust and tonalite for our upper crustal system. And these are calibrated from experiments. Then for our magmas, on the left-hand side, we have our basalt. That's from a relatively recent paper of Nandetkar et al. And on the right-hand side, we have our more evolved magma that's injected in the upper crust, which is we actually use this middle curve. I should use the laser. So we use this middle curve here, which is the crystallization curve for andesite, dacite type magmas. Okay, so first stage here, so we inject stochastically basalts in this shape. So we have dike sill shapes which are stochastically being injected in the lower crust, which goes up to about 17 kilometers depth. And so what you get here is after 4 million years, you get this, you see, and this is the initial stage here. So here is our ISO contours of the temperature, and you see how when you form this lower crustal magma body that you're disturbing quite significantly your temperature in the lower crust, but also in the upper crust, so you're basically pushing your ISO contours upwards. So this is another representation of the same thing. You have depth versus temperature. This is your initial geotherm in blue. And after a couple of million years, you're pushing your geotherm here to the right, so it gets hotter. This is your upper crustal part here. So you can, you're actually elevating your geotherm quite significantly. So we refer to a mature system when actually this geotherm in the upper crust becomes quite stable over time, and this is a criterion we use. So you have this bump in your geotherm, and then it's sort of becomes steady state. And at this point, when it's below 5% change, we call that a mature system. So then what we wanted to compare is then when you have injection in an undisturbed system versus one that is thermally mature. And that's what's shown here. So here on the left we have injection in a thermally mature system, and on the right we have an undisturbed system for the upper crust. Okay, so what's important here is that first of all we can reproduce the previous results of thermal models. So this is Katrina Nen's data points or results from her model. These blue points are from Sarah Gelman's work, and since we're using the same melting curve, we can actually reproduce that one pretty well. So with our undisturbed system, what happens when you have a thermally mature system is that you basically shift your curve all the way to the left by almost by more than an order of magnitude. And also when what happens is that you can now inject for a much longer time, and if you keep injecting from 200,000 years to 2 million years, you can actually start storing a lot of magma in the upper crust. And that's again shown here. It's at the bottom panel here. When you increase your duration, curves go up, meaning you can store a lot of magma in the upper crust in a thermally mature system. So this is a graph that was also used yesterday in a couple of talks, where you have volume versus time, and these lines are fluxes. And what happens is if you have this undisturbed geotherm, which is these purple points, you fall into the a classic classification that you have your super eruptions here, and your plutons fall here below that curve. However, when you have a thermally mature system, you have a very significant change to the right, and you can start producing these very large systems at much lower rates. So it has quite an important impact if you want to use those type of diagrams to infer the amount of metal or amount of copper you would need to form an ore deposit system. So this is conclusions of the first part. Again, so a lower crustal magma reservoir primes the upper crust, and you can start building your long-lived magma storage. We're talking about millions of years here. The critical rate drops by an order of magnitude, and you no longer have to choose between your different types of storages. Initially, when you do not have yet built your lower crustal system, you will indeed have such ephemeral type behavior. As the lower crustal magma body grows, you go to cold storage in the upper crust, and eventually you can even get to warm storage if you just give it enough time to build up magma. So we can explain a wide variety of emplacement rates and durations, and also important to note is that you can explain the emplacement of volcanoes, individual volcanoes and plutons with the same emplacement rates. Okay, so the second part of my talk, I'll actually talk a bit more about outgassing. So, classically, people have talked about degassing. So that's when you form, and we here will talk about outgassing. So the difference, what we mean with degassing, is that you form an exhaust gas phase, and outgassing is that actually you physically remove that gas phase from your system. So that's what we mean with intrusive outgassing. So in the past, people have called that passive degassing. And from these two basic observations, you would infer or would expect that intrusive outgassing is actually more more effective than outgassing by volcanic eruptions or volcanic outgassing. So the first observation is that plutonic rocks are typically dry. They have less than 1 weight% of water. But magma typically contains more than 4 weight% of magma in the upper crust. So how do you go from this wet environment to this dry environment? And so the second observation is that you have a very high intrusive to extrusive ratio, again in arc settings, but between 10 to 1 to more than 30 to 1. So you have a lot more magma that is left behind in the crust, which contains a lot of volatiles. So you would expect, if that becomes dry, that the intrusive outgassing should be more effective than the volcanic outgassing. And in that sense, it's quite important to form your porphyry systems. So what we try to do here is quantify these processes of outgassing by combining a couple of numerical models. So the top model here is a pore scale model developed by Andrea Parmigiani. And this model is pretty much as far as you can get from a back of the envelope calculation, as you can imagine, because it requires the calculation of this crystal structure. You have this melt going through it, and you have these bubbles going through it. So you have to deal with 3 phases and tracking the surfaces of these 3 phases. And then we're going to upscale the results from this model into a magma reservoir model that can account for outgassing and heat loss to the crust, as well as mechanical response of the crust to outgassing, which I'll come back to later, is quite important. And I developed this model a bit earlier together with Chris Huber. Okay, so first step in this pore scale model is that you're dealing with individual crystals here, so you have to build your system, your crystal network first. You do that with a stochastic nucleation and growth algorithm. So here we have 40% crystals, 50%, 60%, and 70%. And once you have that structure, you can actually calculate the intrinsic permeability. So how permeable is such a network? And that's what you do with a single phase flow, so you don't have yet bubbles here in the system, and you see, and you just let a liquid flow through your system, and you calculate the velocity pathways through the system, which is what's shown here. So red means high velocity, and blue means low velocity. So here is the sort of the result of the entire system that you're solving for, your permeability here on the left-hand axis and crystal volume fraction on the bottom. And you see that permeability, as you would expect, goes from high to low as you increase your crystallinity. So now we know our effective permeability, but you want to go a bit further, and you want to know how easy the bubbles actually escape through this crystal network. So when we assume that the time scale of channel formation, so the time scale that it takes to form connected bubble paths is smaller than the time scale of second boiling, then having an initial gas distribution can be thought of as a second boiling event, or coming from a second boiling event. And also an acronym that you'll often see appear is MVP. It's magmatic volatile phase and not most valuable player. But that's comes from earlier work that Andrea has done, and they kind of stuck with that acronym. But you can think of it as the gas phase, essentially. So what you see here is different initial starting distributions of the gas phase, and you just increase it, and we try to run to several scenarios. So how do you get channels? Most importantly, you have 2 competing forces. You have the buoyancy force. Obviously, your gas phase is less dense, so it wants to move upward, but it has to squeeze through this crystal structure, and so it gets resistance from capillary forces. And we estimate that, and that's quantified by something called the bond number, And we find that this, for magmatic systems, is in the range between 0.1 and 1, which is the range we used to look at of parameter space we explored with this model. So what you see here is initially as on the left-hand side, so those two are connected. So this is the velocity distribution on the bottom, and on the top you see your bubble distribution. You have here low bubble or gas volume fraction, and then you increase here. And you see that you need a certain amount of bubbles to actually start forming channels, and when you do form these channels, the transport of your gas becomes much, much faster, which is what you would expect. So what you see here, then you can try and quantify this process, which is what is shown here. Here you have your initial gas volume distribution, again your velocity field where there's no channel formation on the bottom. Same thing, but when you do have these gas channels forming. So this is quite a busy plot, so let's take a moment to go through it. So we have our gas volume fraction here on the y-axis and crystal volume fraction on the x-axis. First thing you should note is these triangles, black triangles, indicate simulations where we do form these channels, and these red circles indicate where you do not have any channel formation. These curves here, SG, means the saturation gas volume fraction, so it's the gas volume fraction relatively to the melt, the amount of melt in your system. So these put up some boundaries. It's basically another way of quantifying how much gas is in the system. Then finally, these are some melt calculations, and these will show you if you have a certain amount of water in your system, how much gas volume fraction will you get based on that starting amount of total water. And you'll see that for 4 weight percent, you will definitely form gas channels, and for 7 weight percent, everything falls below. So you definitely expect gas channels in that situation. On the bottom here, you see the same thing, but for different bond numbers. So again, that's the gravitational force versus the capillary resistance towards gas movement. And you see that for this green curve here, when you have low bond numbers, so capillary stresses are actually quite important, and they resist or they hinder the movement of the bubbles. And for a higher bond number, it becomes more easy to form these gas channels, and these curves drop downwards on this graph. So there's another mode of gas transport, and it's that doesn't come from second boiling only. It's injection from gas from below, for example, by a new intrusion. So we also looked at that scenario and see how easy you form gas channels in that way. And turns out, so we simulated that you have a sort of infinite gas reservoir at the bottom, and that feeds into your crystal structure. And the result here, shown here on the left here, is MVP volume fraction versus crystal volume fraction. Again, the same thing as before, but you see that you need much less gas to form gas channels. And that's because you're not dealing with all those dead gas bubbles that do not interact with the gas channels as in the second boiling case. You actually are more efficient in creating those gas channels. Okay. This is a comparison between the two modes of gas channel formation. We have our second boiling event, and here at the top, which is again your bubble distribution and your velocity field. Same here at the bottom, but in this case from injection from below. And the difference is again that you need more gas essentially in the second boiling case, just because you're dealing with a lot of bubbles that do nothing, just stay where they are, because they're trapped in the crystal network. And we do this for several bond numbers, essentially. It's bond number 1, at the crystal volume fraction of 0.7, and this is slightly lower crystal content, bond number 0.5. Okay, so now we want to translate that into a larger model. So how do you get your gas out into your from the magma reservoir into your surrounding crust, which, if I understood talks of the last couple of days, is really important to form your ore deposit. So first thing you want to quantify is the discharge rate, so the speed at which the gas travels once you form these gas channels, and that's what's quantified here. And so these lines here you can rather easily translate into the model. Second thing you need is the relative permeability. So I already showed you the effective permeability calculations. The relative permeability is just the amount of gas of the permeability of the gas phase, which is actually a transient feature, but for the sake of translating that to our larger model, we keep that as a static quantity that's just dependent on your crystal volume fraction and your gas volume fraction. So what are the modes of outgassing then that we're going to use? And we try to sort of summarize this in this ternary plot. So here on the left-hand side, we have our MVP volume fraction. On the right-hand side, the crystal volume fraction, and on the bottom, our melt volume fraction. We have this white area here, and that's when you have more than 50% gas, which is not really relevant for our case, but it can be relevant when you have these explosive volcanic eruptions, and the MVP becomes a carrier phase. This blue region here is when you have bubbles moving upward just due to buoyancy, but they're not forming gas channels because you don't have a crystal structure that actually forces these gas channels to form. When you hit this threshold here, you enter into this grayish region where you can start to form these gas channels because you have enough crystals to support the structure and push these bubbles into this channel formation. But of course you need to have enough gas to do that, and if you're below this amount, you're in the green zone, and then you have these trapped bubbles. Of course you can still move the gas in this case, for example through something called capillary fracturing. And we think that this is only going to be a viable mechanism when you're at really high crystallinity. Some simple scaling arguments will tell you, based on the surface tension, on the friction of your crystals, and on the confining pressure of your magma reservoir, that the pore throat size needs to be on the order of nanometers, which is really tiny, which only will be achieved at very high crystallinity. So you can, we did not implement this in the larger model, and we just set the gas loss in this green region to 0. Okay. So what did we actually simulate with the larger model? So imagine that you're starting off with this magma lens in the upper crust where you have a mobile magma, and we just let it cool. We don't have injection of new magma, just for the sake of simplicity. We look at this scenario only. So we have monotonous cooling of the magma lens, and the model accounts for second boiling. So as you crystallize, you're pushing more volatiles into the melt, and you're creating more gas volume due to that. So initial water content is 5.5 weight%, and we're at the depth of 200 megapascals. What you see here, this graph is just to point out that the crystal volume fraction is actually a good proxy for the cooling time scale. So if you normalize your actual time to the cooling time scale, which is related to the size of your magma body, then you can see that the crystal volume fraction versus time actually follows pretty closely in between different types of simulations. So we're going to use that in our plots later instead of time. So another thing that I want to point out is the different scenarios we're going to look at. We have these two scenarios. The blue curve is a cooler crust, so a colder crust, and a red curve indicates a more mature reservoir, or more mature reservoir. And here on the right-hand graph, we just look at the different sizes of the magmatic lens from 5 cubic kilometers to 500 cubic kilometers. Okay, so with this rather simplified model, you can see that you also already have some very interesting behavior. And what we're looking at here is chamber pressure and gas volume fraction. So actually one point that I want to make, so I saw a lot of talks where pressure is used just as a sort of one-to-one correspondence to depth, but actually in the magmatic lens and many places the pressure will vary locally relative to the lithostatic pressure. And it can vary quite a bit if you're starting to move gas around. And that's actually what's shown here. So on your top left we have overpressure, so that's the pressure difference between the surroundings. And what you see here for the blue curve, which is the colder crust, you start increasing your pressure, so meaning that second boiling actually creates pressure, and the gas loss cannot compensate for that loss, so you have a slight increase in pressure, but then you have this sharp drop in pressure, and that's due to the fact that you're starting to form channels. And when you have these channels, these are extremely effective at transporting gas because the viscosity that you have to overcome drops by many orders of magnitude. So gas bubbles have to push the melt around, surrounding melt to get the gas moving upward. And so that's on the order of 10 to the 6 Pascal seconds. While if you have these gas channels, you're just dealing with the viscosity of the gas phase, which is on the order of 10 to the minus 5. So that's quite a significant change in the rate of gas transport. And what happens is that you have this sharp drop, but all of a sudden you're hindered again, and that's because you're below the lithostatic pressure, and that lithostatic pressure will start containing the gas bubbles inside the chamber. So the pressure gradient between your reservoir and the surroundings will actually hinder the movement of gas. And that's what's happened here. So you flat out, and then at some point you increase your pressure again. And that's because you're reaching the saturation limit. So, at this point here, you're hitting the saturation limit, which you can calculate theoretically. And basically, you're at the boundary where you have gas channels and you don't. And you follow that boundary all the way through to the high crystallinity at 0.7. And then we stop the simulation at 0.7, but then we note that you can have potentially gas transport due to this capillary fracturing mechanism. Okay. An important thing to note here is also the mechanical response of the crust. So a hotter crust will actually accommodate much more easily for the pressure changes. So you don't have this rapid increase in pressure, and you have this bounce back, while in the colder crust you actually stay flat at the bottom here. And that's because you have an elastic response rather than a viscous response. Same thing for having a larger magmatic lens, 5 cubic kilometers. You have this more elastic response, while for a very large system in orange, the 500 cubic kilometers, you'll have a very viscous response of your crust, and you follow the saturation limit. What you see here at the bottom is the actual volume fraction in your simulation versus the crystal volume fraction. The black curve indicates the limit of the threshold calculated from your saturation. And the red curves indicate, again, this effect of the mechanics of the surrounding crust, which will actually act to hinder outgassing. And if you have a very elastic response, you'll have a lot of trouble to get the gas out. And again, for the size differences between the magma chambers, if you have a small chamber, you'll have an elastic response. It's very difficult to get the gas out in that case, while a very large chamber, it's much more easier, and you'll start, again, to follow the saturation curve. Some more data on these simulations here. So here, this might actually be most interesting for the porphyry side of things is that you have your total volatile mass fraction versus crystal volume fraction. And initially, so the black curve again is your saturation limit. And so this is the maximum amount you would be able to get out if you don't have any mechanical effects. And the red curve is your hotter crust, and your blue curve is your colder crust. And you see that you go from this initially 5.5 weight percent all the way down to about 3.25 weight percent. So important to note that you're left almost with more than 3 weight percent of water right at the high crystallinity. So if plutons are dry, you still need to get a lot of water out in this region here, above 70% crystals. Again, same story for looking at the different sizes. The large chamber here is the one that closest follows your saturation limit, and but even in that case, you're left with a lot of water at high crystallinity. Another interesting point to note, or what you can do, is look at what crystallinity window is actually your outgassing most efficient. And what you see is here at the initial formation of your channels, you'll have a lot of gas loss, a sort of peak in gas loss, and then it sort of drops down all the way to the higher crystallinities. You could imagine that you could have another peak here when you start to have this capillary fracturing. So potentially this could be interesting if you want to look at partitioning of different elements which are related to certain crystallization mechanisms. So this is the conclusions of the second part. So most of outgassing is most efficient when you're in this mush state and not when you have a mobile lens. A majority of the volatiles is released at intermediate crystallinities. You will have this channel formation, but at even higher crystallinities, which we infer that this should be the most efficient mechanism of losing your gas. You'll have 50% or even more of the volatiles that you'll need to lose. You have a lot of important mechanical effects that come from your crustal response. So crystal content is important, but you also need to take into account your mechanical coupling, which will act to hinder your outgassing. And then perhaps, I just put a question mark here, but perhaps interesting for the porphyry copper system, if this is true, then you might think that the porphyry copper systems will actually have their largest growth at the end or the waning stages of your magma or reservoir life, rather than when it's erupting a lot of magma. So that's something that I just threw out there. Maybe you have thoughts on this. And with that, I think, yeah, I leave you with that. These are just the references of the two projects that I presented. Thanks very much for your attention.
Thank you much for an excellent talk. Are there questions? John.
That was really interesting. Going back to the first part of the talk, you put those stochastic dike sill things that look like little T's into the lower crust. What's your criterion for them then for leaving the lower crust and moving to the upper crust? What actually triggers the ascent from the lower crust to the upper crust?
So that's imposed. So we're not actually calculating. So we're extracting just the amount of energy. We just make sure that our energy balance is correct, but we don't actually have, like, we impose the emplacement essentially, just like other thermal models. So we don't calculate the actual movement of the magma. So this is emplaced.
So you can actually have any transfer rate from the lower crust to the upper crust.
Yeah,
You just make up a number.
We do a parameter range, and we have obviously the limit of the amount of melt that is available in the that's our maximum amount, or duration and our rate are limited by the amount of melt that is created in the lower crust. That's our
I see. Okay.
criteria.
All right, thanks.
Thank you. Very interesting talk, Wim. I've a question relating to the second part of the presentation. If I understood correctly, the magma you were modeling is a sort of unit volume of magma which stays thermally homogeneous during the course of crystallization.
Yes.
So I was wondering if you expand this model on the unit volume of magma to a real magmatic system, which in a sense is thermally zoned because it's trying to keep up with a cold crust, would you, how different would this be? Because your last conclusion or inference on porphyry copper was that it would you would degas on the vanning stage of the system, but this high crystallinity they would already be established quite early at the periphery of your intrusion.
Yes. So there's our first order models, and there's always room for improvement. And adding the spatial component is obviously something that can alter results. To what degree, I don't know, but it's definitely a direction I want to work in. But the fact that I can give you the reason why I make that assumption is because I want to have the mechanical coupling with the crust, and that's why you reduce your spatial dimensions. So this will have an effect. I cannot give you the answer as to how much that will change things. But I'd like to work on that for sure.
Thank you.
Any more questions? Thank you very much.
Thank you.
Excellent talk.